It's a great pleasure that I'd like to introduce our first distinguished speaker, Professor Krishnaswamy Ravichandar from the University of Texas.
I want to start by thanking the organizers for inviting me to give a talk at this exciting symposium. I grew up about 15 miles south of here in Camberra, and it's nice to be back here visiting even for a very short period of time. Today I'm going to talk about fracture in hydrogels. So completely continuum-based modeling and experimentation. So the only scales that will be bridging are time scales between porous flow and viscous deformation. Will not do any scaling of length. This work was done jointly with my former graduate student, C. Chan, who's gone on to become a postdoc working on plant biology, mechanics of plant growth. But I get to talk about the exciting work she did in Poroviscoelasticity. And so let me start. Hydrogels are interesting materials because they are composed of long chain molecules that are networked, but inside of them they hold water. So there's a two-phase material, and the interaction between the deformations of the molecules and the flow of the water leads to interesting mechanical behavior, both in terms of deformation response and fracture response. And I want to go over some of those ideas today. The applications are numerous. We engineers like to motivate ourselves by saying we do something that's of interest eventually. And in this case, these are used in contact lenses, probably used as cartilage replacements, soft robotics, drug delivery, and a host of other problems. But the main material that we're going to be concerned with is that colored orangish cube, jiggly cube that you've all seen as Jello dessert that we eat, made out of collagen mixed with water. So it contains of three ingredients in our implementation: collagen itself, water, and glycerol. We add glycerol because all of our experiments take on the order of 3 to 10 days, and they're done at room temperature. And collagen is food for many, many bacteria and fungi. And so if we don't put something to inhibit growth of mold and things like that, the specimen gets eaten away in a couple of days. So we mixed a little bit of glycerol in the composition. But it also does an interesting play on the material behavior. Glycerol is viscous, water, and so it's going to create a response that is highly viscoelastic. This is it. The way we do this is to mix gelatin with 51% all the weight of glycerol, 34% water, making the entire stuff. Heat it up at about 80 degrees Celsius or so, mix it thoroughly, put it in the refrigerator, and the next day you get your specimen all gelated and set up. And then you can cut it into whatever shapes you want to do the testing, the mechanical characterization of the material. A little bit about the structure of the material. The native material is collagen. Collagen is a triple helix composition, and in crystalline state, it would be the three helices intertwining and making a collagen molecule of some length. If you denature it by heating it above a certain critical temperature, it liquefies, melts, and you have random coils of collagen molecules, not anymore in triple helix conformation. If you have low concentration of collagen and you cool it down, it forms very few nuclei where it forms the triple helix. Typically, it forms a triple helix on one molecule, and then it slowly grows along the length of the nucleus and becomes individual collagen crystallites. If you cool it faster, there are little nuclei that appear, and you get some defects in the conformation as they grow up, and you see a structure that looks more like this. If the concentration is very high, there's a likelihood that three different molecules are right next to each other. They can form a nucleus of the triple helix. And depending on the nature, speed of the cooling, you either get a full triple helix of single one packed again, or a defective material with little segments of crystalline material with amorphous regions thrown in between them. This is the preferred state because it's able to accommodate, it's like a network polymer now. The triple helix regions look like crosslinks, and the amorphous regions are able to move around more easily, and so it looks more like a rubber in that sense at macro scale. And so this is the kind of material we make by controlling the concentration of the collagen and by controlling the cooling rate, and we get little pieces like this. Now, two things can happen in here. This is a cartoon of what might potentially happen. On the left side is the zoom in of one region of the molecule. These are collagen molecules. These are water that are trapped in there. This structure that is set up here can trap a large amount of water within itself by just weak bonds. Two things happen. One, if the concentration of water outside is large, it can push the water into the structure. And so migration of solid molecules into the solid is one process that is possible. The other possibility is that when you apply a stress on it, the molecules move around in the medium and they exhibit a viscous response. And so you could have a viscoelastic rearrangement of the polymer chains. Turns out both of these happen, and there's a terminology. If it's just solvent diffusion, it's poroelasticity. If it's solvent diffusion plus viscous rearrangement of the molecules, is poroviscoelasticity. And both of these intervene in the fracture problem eventually. So what I'm going to do is first go over some experiments and modeling of the poroviscoelasticity, and then finish off with some observations on what happens in fracture and how one can understand and characterize fracture in these materials. There are two time scales in this process. One is the time scale of migration of the water molecules, solvent in general, and the other one is the rearrangement of the polymer molecules through viscous processes. On the horizontal axis, I've drawn time normalized by the viscous time scale. If you're in the very short region, very short time scale, the viscous processes are not resolved. They're still going on, but if you wait long enough, the viscous processes have completed. On the vertical axis, I have a length scale and the diffusion times scale, d, diffusion times diffusion that occurs in the viscoelastic time scale. So if you're in short length scales, diffusion can complete itself and your poroelasticity is fully resolved. But if you go to very long specimens, poroelastic diffusion hasn't completed, and you'll have an effect based on that. If you're at intermediate length scales and time scales, you have a coupling between what happens in porous flow and what happens in viscous deformation. And people have looked at characterizing this through a number of different experiments. One is to do a confined compression, let the solvent come out and hold it while the stress relaxes, pore pressure relaxes as the solvent migrates out, and then do an inverse calculation to see what the poroviscoelastic properties are. Similar thing with an indentation with a spherical head and so on. All of these are very difficult experiments to perform, very difficult experiments to diagnose, and harder to interpret because you always need a model to figure out what's going on. We decided to do something very simple. Do uniaxial tension and diagnose it with image correlation methods so that you can monitor the strain as a function of time, and then do a coupled experiment with viscous deformation as well as porous diffusion and see if we can resolve what's going on where. So the idea is to take the chamber and control the humidity in the chamber. We're not going to put the specimen immersed in the solvent. We're going to put it in humid environment where the solvent is not in liquid form, but it is in vapor form outside the specimen, but it's in liquid form inside the specimen. So we control the temperature and the humidity in the chamber. And then we put in two specimens in there, fixed at one end, and a dead weight hanging on the other one for it to allow creep. Two specimens experience the same thermal and hydral environment, but the one on the left side is going to swell or dry, depending on the humidity levels. And at a certain point in time, we're going to add a load on it to start the creep process. The specimen on the right side is going to be a control one, which is just going to be exposed to the humid environment and temperature, but no mechanical forces on it. By comparison of what happens to these two, we should be able to extract out what is poroelastic and what is viscoelastic. The rest are details, but we do decorate the top surface of the specimen with a collection of titanium dioxide powders on micron scale particles, and we're able to image that with a camera, keep taking pictures every 10 minutes or something like that over a time frame of about a week in order to see the entire diffusion process as well as the creep process. And from that, we could calculate the stretch in the vertical direction of the direction of loading and the stretch in the transverse direction due to Poisson effect, the transverse contraction. We're going to assume that in the thickness direction, because of the uniaxial nature of it, the stretches are equal to what the stretch is in the width direction. So some results from this experiment. The first one is at a relative humidity of 73% in the chamber. We have two sets of results. The dashed lines correspond to the witness specimen that is subjected only to the hydrothermal environment. So at 73% relative humidity, the specimen doesn't really swell. It doesn't elongate. It doesn't widen. It just maintains its total. You can think of this as the stretched lambda y. It doesn't change much from 1. At this time instant, about 70 hours or so into the process, the second specimen was loaded by a dead weight of a few hundred newtons or something like that, 0.2 newtons, I think. There's an instantaneous elastic response. You add a weight, it stretches by its current Young's modulus, and it contracts in the wide width direction. With time, it exhibits a creep strain, and this is the creep process. If you change the relative humidity and make it 60%, there's not enough water in the chamber. The water contained in the specimen is larger, and it ejects the water out into the chamber, and the specimen is drying. This is what we do in Chennai when we put your clothes out to dry. The humid environment is less humid than the water content in the cloth, so it's ejecting water out. So it's now drying. The lambda, the stretch is less than 1. It's shrinking. And the control specimen levels out at some point when all the water has been ejected out. The loaded specimen has instantaneous elastic response and creep. The one in between is a relative humidity higher than 73%. Now it's swelling. The stretched lambda y is larger than 1. And the loaded specimen exhibits instantaneous elastic response and further creep deformation. This is all the experimental result we have. We have a set of these at different humidity levels and so on, but this is it. We need to be able to understand the poroviscoelastic properties of the material by this. But a lot of information is embedded in there if you're able to tease it out. So this is a cartoon of the initial specimen in the dotted line, the deformed specimen at any instant in time in the solid line. After time t, it's elongated, contracted in the transverse dimension, and we have a history of all of that. And this doesn't make any sense. We can't interpret this the way it is in this representation. But if you decompose the total deformation into two parts, one that is volumetric and one that is deviatoric, you can take the deformation gradient tensor. Lambda x and lambda z are the same. Lambda y is the stretch in the vertical direction. You can decompose it into a volumetric part and a deviatoric part, and then see what happens. And simple calculation shows the volumetric part is lambda y lambda x squared, and the deviatoric part is lambda y to the 2/3, lambda x to the minus 2/3. But magic, everything resolves itself if you do this in this particular representation. This is a very dense slide, has lots of information in there. I'll walk you through it. On the left side is the volumetric deformation as a function of time for about 80 hours. The dotted lines correspond to the specimens without any load, mechanical loading, only thermal, only hygroscopic loading. The dotted line here corresponds to a relative humidity of 73%. The volumetric deformation doesn't occur. There's no swelling, there's no drying. The specimen is in equilibrium, hydrothermal equilibrium with the moisture outside. There's no diffusion going on at all. This specimen is at a lower humidity outside, it's drying, and these are all swelling at different rates depending on the outer humidity, larger than 73%. The solid lines are the corresponding results for the specimens in which load was applied at about 25, 30 hours or whatever it was. You don't see any trace of that in the volumetric response. Adding the extra load, the additional deviatoric deformation, has done nothing to the swelling problem, meaning that the swelling or volumetric deformation is completely poroelastic and it has no viscoelastic effects whatsoever. Then on the right-hand side, we have the deviatoric response from the same set of experiments. The dotted lines correspond to all of these experiments. We calculate the deviatoric response. There's no deviatoric strain at all. There's no shearing. It's just swelling from the humidity. But as soon as you apply the loading, there's an instantaneous elastic response whose magnitude depends on the external humidity, because the modulus of the material depends on how humid it is at any given instant. And then there's creep response. The specimen is slowly elongating as a function of time, but this depends on the outer humidity, meaning that the viscoelastic process depends on the hydrothermal state of the specimen. The amount of moisture will influence how quickly or slowly the relaxation can occur. And this is easy to understand physically. The more moisture you have in the specimen, it's swollen more, the mobility of the molecules is higher, the viscous relaxation can occur faster. It's a power law creep, basically. If you take all of these creep curves and try to fit them, a power law fits them the best. Multi-exponentials can do the same job, but not effectively. A single power law expression like this captures the observed response over a time span of about 80 hours or so. So we think that the creep is occurring at as a power law process. And this particular level of humidity, 73%, there's no swelling, there's only creep. That's the pure viscoelastic response, unadulterated by the moisture diffusion process into it. So this is it. Now we need to create a model to represent this behavior that says swelling is going to be completely poroelastic, shearing is going to be completely viscoelastic. What kind of a constitutive model can capture this? It's going to be some heavy continuum mechanics in here, but let me see if I can walk you through it fairly quickly. This is the initial state here. And after you apply the hydrothermal mechanical loading on it, the final state is something like this. It's sheared to some level and it's swollen to some level. But you can decompose that into a volumetric deformation that is completely hydro, and an isochoric response that's completely shearing. We've already demonstrated that this is only from poroelasticity, so all the viscoelasticity resides in here, which means you can decompose the isochoric response into an elastic response and a viscous response. This is the part that's going to dissipate energy. This is going to store energy and should be able to recover it at some point. All of the volume expansion occurs only by the fact that it's absorbing water molecules from the atmosphere. So the Jacobian of this transformation is going to be 1 plus the volume of the water molecule times the concentration of the water molecule. The total amount of water molecules that go into the specimen will dictate how much the specimen is swollen. So we use what's called a two-potential formulation for viscoelasticity, poroviscoelasticity. We use two functions, basically. One is the free energy density of the body that depends on the deformation, the total deformation, the concentration of water molecules in the solid, and the amount of viscous deformation that occurs at any given time. The second one is called the dissipation potential, and this accounts for how much energy is being taken away from the system, and this depends on the viscous part of the isochoric deformation gradient, as well as the rate at which that viscous part occurs, because this is a time-dependent, rate-dependent process. The two are coupled with a consistency condition saying that whatever energy is recovered from this by the viscous deformation process must be dissipated by this one, because there's no way to destroy the energy that is created by this viscous process. Conservation of linear momentum gives you this equation, where S is the second pure stress, and the mass balance gives you the Darcy type equation. The rate of change of the concentration and the flux out must balance each other with suitable boundary conditions. On top of this, we need constitutive relations to connect the deformations F, FV, etc., and the stresses. And this comes by using the second law of thermodynamics, saying that the net dissipation must be non-negative. And that gives you a definition of stress, that the gradient of the free energy gives you the stress. The gradient of the free energy with respect to the concentration gives you the chemical potential. This says that the net flow must be in the direction of from high concentration to low concentration, but that gives you a definition for the net flux in terms of the gradient of the chemical potential through a tensor that is the mobility tensor, or the diffusion in 3D, for this material when it's in the reference configuration. At the deformed configuration, which is where the flow occurs, you use just a standard diffusion model based on the diffusion constant times the gradient of the chemical potential in the current configuration, deformed configuration. You map it back to the reference configuration, becomes anisotropic, that the diffusion in the direction of tension is larger than the diffusion in the transverse direction, and so on. But those are things that can be managed in the framework of finite elasticity. So that's the general framework for forming the boundary value problem, closing the system with constitutive equations. So we need to find specific forms for the free energy density function and the dissipation potential. You do a simple Legendre transformation to eliminate C in favor of chemical potential. So you rewrite the free energy function in terms of the deformation gradient, the viscous deformation gradient, and the chemical potential. Now we need to dream up of functions that will be a suitable representation of the poroviscoelastic process. Typically, this is done by taking the free energy function and decomposing it into many parts. There's an equilibrium volumetric part that doesn't depend on time, it's just the swelling part. There's an equilibrium isochoric part, which is when the complete viscous dissipation is finished, there's still an elastic energy in there as the equilibrium part here. This is the non-equilibrium isothermal. So there's this, with the dissipating part, there's a spring that is attached. So that gives you a third term. And the last one is from mixing of these different species. We have three components: water, glycerin, and gelatin. So that gives you a mixing energy based on a model from Freud. And so we put them all down, give them forms. The volumetric part is going to be quadratic in the volume expansion. K is a bulk modulus then. The isochoric part, the equilibrium component of that, is going to be a neo-Hookean material. So G is the shear modulus of the material, of the elastic branch of the material. Similarly, there is a neo-Hookean part for the viscous branch that has a different shear modulus. So there's a spring and dashpot in parallel. G is the spring constant for the sole spring, and GV is the spring constant for the spring dashpot branch of it, and so on. The dissipation potential has a particular form. It's derived from a velocity-dependent function, but it has one material constant that defines it. This is the viscosity of the branch. And so the ratio of the viscosity of the spring side of the branch and the shear modulus of that same branch gives you a time constant. This is the viscous time constant of the spring dashpot model. It's written in terms of the Wright Cauchy-Green stretch tensor, or the rate of the Wright Cauchy-Green stretch tensor. We're keeping everything within the framework of finite elasticity because finite deformations, because the structures, when the swelling is large, maybe in the range of 30 to 50%, and when it dries out, can be even larger than that. This is something I'm going to skip. Yeah, the viscous model is based on a fractional derivative, and it's just too dense to go through this early in the morning. But it's basically something that says that the parallel law of viscosity that we found for the creep process is going to be represented in the finite stretch domain by a fractional derivative model, where the fractional derivative of the viscous branch of the stretch tensor is going to be given by this part with a time constant, viscous time constant tau, to be calibrated. The term beta is also to be calibrated to give you the right parallel law of viscous creep response. All right, so that comes with the set of governing equations. The first one is the work done by the stress. This is the work done by the external body forces. This is the work done by the external tractions. These are work rates. So that's force balance, or energy work balance, written in a weak form for in terms of the test functions. This is the diffusion equation, or the mass balance equation. The term with the T is the value of the Jacobian at time of the flux at time step T, and everything else is at time step T plus 1. So we've written an incremental form of the mass balance equation. And this is the equation for evolution of the viscous strain through the fractional derivative model. So there's a ton of material parameters in these models, things that describe the free energy, things that describe the dissipation potential, things that describe the fractional derivative evolution of the viscoelastic part, and so on. So the question is, how do we calibrate these constants? So first thing to do is to implement this numerically in a framework. We did that within what's called Phoenix, an open source general purpose solver, where all you do is you provide your governing equations. It has the infrastructure to discretize it and do the solutions. But we do need to look for stability of these solutions, and in order to do that, different kinds of discretizations are used for different functions. The displacement field is discretized by a second-order Lagrange interpolation function. Chemical potential is discretized by a linear function within the same element. And the internal variable, this viscous component of the strain, is considered to be constant in each element. That means there's a discrete jump between the strain rate in each element. And turns out this is the one that leads to a stable solution procedure. It's well established, and so we use that. Backward Euler time discretization for the diffusion problem or mass balance problem. The numerical evaluation of the fractional derivative is a big challenge because it needs information at every point from all times previous to the current time. And so it's a large storage requirement, but it's something that can be handled in modern computers. Initial and boundary conditions are important. You need to describe the chemical potential state of the specimen, meaning how much water is contained in the specimen at the onset. And then the other boundary conditions are based on displacement and tractions for the forces. and for the chemical potential and fluxes for the water content. There is an interesting thing that happens in the boundary condition for moisture flux. If you think the chemical potential in the interior of the specimen is constant, chemical potential is going to have a gradient as it approaches the free surface. It cannot be a step function jump across that. And the chemical potential on the outside, let's say, is at some uniform value. The exchange between these two, you can use a Dirichlet boundary condition which says that the chemical potential here must be equal to the chemical potential. I lost my feedback. Okay. Can you hear me? All right. Chemical potential at the boundary must be equal to whatever it is on the outside, right? That's the Dirichlet boundary condition. Or you could have a flux condition saying that a certain amount of moisture is either being ingested or extracted from that surface. Neither one of those is true for this swelling drying experiment. We have liquid water here, we have vapor here, and so it has to have a solidification or condensation and then a diffusion process, which is going to take some time, which means the boundary condition is going to be more like a heat transfer condition or something, or a Robin boundary condition, that the flux is going to be proportional to the difference in the chemical potential. So it's more like the flux proportional to the difference in the chemical potential. That brings in another constant into the material model, and all of these other things here are to account for the large deformation problem involved here. So we have a code that has all of these material constants to be calibrated and could be solved for whatever the boundary value problem is. So we did 3 cases. First one is don't apply any load on it, just the diffusion problem. The second one is apply a load but keep the chemical potential constant so that there's no water exchange. It's just a pure creep problem. And finally, the mixture of the two. Luckily, we know how to do these things because the first one is easy. Don't apply any load on it. It's just diffusion. The second one, we have found a way to do this by saying if you keep the chemical potential at 73%, there's no moisture exchange between the specimen and the surroundings, so it would be just the pure creep problem, and so we could do that. And in the interest of time, maybe I still have some time, right? Okay. First case is just the swelling problem. Swell it until it reaches equilibrium, or dry it until it reaches equilibrium, and find the connection between the chemical potential and the final dimension or the stretch size of the specimen. The stars are experiments. The line is the calibration curve that passes through. As a result of that, you calibrate the bulk modulus K and the 2 constants in the Flory mixing model for the free energy. And so you can calibrate those constants. The next one is to look for the diffusion. And now we go for just the water ingestion or egress. And the symbols are experiments. The solid lines are calculations of the volume expansion or drying with a single diffusion constant put in there and a value for the coupling between the flux and the change in the chemical potential, so the alpha R parameter. So we calibrate those from there. Then we go to case 2 where there's just creep. And you can do a calculation, but the closed form calculation of that problem. But the main idea is we have the experiments and symbols, and the solid line is a calculation of the response, extracting the viscous time constant T sub V and the order of the fractional derivative beta. This turns out to be on the same magnitude of the creep exponent that I showed you when we did the experimental results plot. The power law there was about 0.6, I think, and this is close enough to that. So we have calibrated all of the material properties. There's one more thing to do for the cases when there's both mechanical loading and hydro loading. Could we represent everything? And it turns out you can. This is the same program. The symbols are experiments, the solid lines are the fits. But this time, we have to change the viscous time constant for each one of the swollen specimens by a factor that depended just on the swelling ratio. So if I increase the volume by swelling to a certain volume, creep process will speed up in proportion to that increase in volume. That's what this says. The time constant of the viscous process multiplied by the volume of the specimen is constant over the entire time. And so we're able to capture the poroviscoelastic response with this two-potential model fairly easily, accurately. All right. How much time do I have? 10 minutes. Okay. That's the poroviscoelastic story. Now there is a fracture part to it. What happens when you take this material and subject it to loads that generate cracks? In the interest of time, I'm going to forego a description of the history, except to say that the main idea behind fracture of these specimens or materials is that there's a process zone that's created near the crack tip, and this process zone could be influenced by both viscoelastic processes and poroelastic processes. The diffusion of water into or out of the crack region into the process zone should have some effect on the rate at which the cracks grow. So first, some experiments. This time we use what's called a simple shear experiment for strange reasons. But the idea is you take a strip of this material, clamp it between two rigid boundaries and displace them vertically, insert a pre-crack in there, and then let this thing do whatever it wants to, diagnose it, and figure out what you did to it to extract fracture properties. What we did was, instead of driving it at constant rate, we applied a constant force on it so that the process would be one of creep, viscoelastic creep, and then poroelastic diffusion. We decorated the specimen with these titanium dioxide particles, and you can see what happens. So I'm going to distinguish between a number of different cases of loading. They're all constant humidity environment, dead weight loading. But in this case, the relative humidity was smaller than the equilibrium humidity of the specimen. And so the specimen is going to dry over time. And if I load it, there's an instantaneous elastic response. There's some creep. The time scale went from a few seconds to now about 60 hours. Nothing happens. Crack doesn't grow. In fact, the specimen shrinks and just it can hang on elastically forever until the specimen degrades, I suppose. On the right-hand side, it's the same specimen. It's at a humidity that's in equilibrium with the specimen, and so there's no diffusion. But it's at a slightly higher load. And what happens here is as soon as the load is applied, it reaches critical state and the crack starts to grow. Now in this specimen, because of a dead load, as the specimen crack increases, the work done by the weight increases, the crack is continued to be loaded, and so it runs away. Now these are all accelerated. They're moving at microns per second, microns per minute, right? They're accelerated, time accelerated. So this totally took about 5 minutes. So these are two ends of it. One, there's no cracking whatsoever, and here there's instantaneous response. The instantaneous response would indicate that the poroelastic effects are going to be minor, because you remember the time scale for diffusion was on the order of hours or days, and in a matter of 2 minutes, it's not going to diffuse the water anywhere. It can create forces because the water is in non-equilibrium state, but it's not going to create any energy there. The last one is what I've labeled case 3, is at equilibrium humidity. So again, there's no poroelastic diffusion overall, but the load is such that the crack remains stationary for about 470 minutes, and then it starts to grow, and it grows fairly rapidly. In the next few minutes, it goes over the entire length of the specimen. So as you increase the load, the crack starts to grow sooner and sooner, but as you decrease the humidity, the crack growth rate keeps dropping significantly. So that's all the experiments are going to tell. They're going to allow us to calculate some deformation fields and basically energy flux and things like that. But we need a model in order to proceed further to interpret what went on in those experiments. 5 minutes? All right. So we resort to something called the Shapery's theory for viscoelastic fracture. The original specimen is subjected to some stress state at every point, displacement state, and there's an energy distributed at every point based on that deformation state. And it's subjected to some tractions, forces, external loading. What Shapery suggested was that corresponding to this, at every instant in time, there's a reference elastic problem to which you can map everything by simply assuming that the reference state is going to be some viscous manipulation of the current state. In the particular experiment that we did, and this is the reason we chose that, is a traction-controlled experiment. Forces were prescribed, not displacements. And in this case, for a two-dimensional problem, there's a rigorous theory that says that the strain fields and the stress fields are exactly the same in the current state and in the reference elastic state. So the reference elastic state stress is the same as the current state in the actual specimen. But the displacements in the reference state are related to the displacements in this current state by a convolutional integral that incorporates viscoelasticity in there. You could incorporate any viscoelastic model into this particular thing. We've just used a linear viscoelasticity because we're going to apply this at the far parts of the specimen away from the crack region. The upshot of this is that you can create what's called a contour integral, where if you take this product of your field quantities and integrate over a contour that starts at the bottom of the crack, goes around this crack tip, and comes onto the top of this crack tip, it's independent of the path along which you make this calculation. So you would take one path that is far away from the crack, and you evaluate based on the displacement measurements that we've made using the image correlation method, and you can calculate this integral at the far field. But if you take another contour that's right along the fracture process zone, you could do another similar integral, call it J sub f, and it can be represented as what the work done by the tractions that appear only on this line. So this is something that, and the two are equal. So if you measure far field displacement and strain quantities, you can calculate what happens in the fracture process zone, and that's the thing we use to be able to characterize the connection between the applied load, represented only by this far field elastic integral, and the local dissipation, represented as the work of fracture. We extract that in terms of the measurement from the far field. I'm going to skip through these and show you what that final result is. That effective integral JV, which is the flow of energy from the outside into the crack tip region that's dissipated in the crack tip region, is here in units of joules per meter square, and the speed of the crack measured is down here. So both of these are measurements. These J calculations come from calculating the stress and strain field everywhere in the specimen along that contour, and the velocity measurements are from finding the position of the crack at every time instant. And they all collapse. It doesn't depend on the magnitude of the loading, the humidity state, and so on. They all collapse into one curve. You squint your eyes a little bit. And this now is a failure criterion for the viscoelastic part of the material response. Because we've done these experiments at different humidity levels, poroelastic effect, if it is embedded in it, is included in the JV, but it seems that this is not a systematic variation, so we think it's not, the poroelastic aspect of the fracture energy is not a large contribution to the overall fracture process. All right. I'll stop with one final slide. This is an estimate of the energy that's dissipated in the fracture process zone. So on the order of 10 to 100 joules per meter square, depending on how fast you're on the crack. Can we play with the humidity and get the fracture energy to become lower? And so we did the same experiment as before, hang the dead weight on the specimen, but after a few minutes, attack the process zone. Diffusion is very slow, doesn't allow you enough time to get the water molecules in there. Inject the water. Just put a droplet of water on the fracture on the back side of the crack. The water is immediately available to the fracture process to start unraveling, and this is what happens. It's opened up, and then a drop of water, couple of minutes, and the crack starts to run. As it runs, the meniscus follows. The water follows with that meniscus being driven there, and so it lubricates the crack process zone continuously until it runs out of water and the crack stops. We can do the same calculations of the J integral for this process, and this is what happens. It's the same material, but now it's weaker. For the same value of the driving energy, it's going faster, meaning that the fracture process zone is dissipating less energy, and so you can influence the fracture energy by controlling the moisture content in the process zone, not in the specimen in the far field. That diffusion is slow, but this ingestion is faster. All right, with that, let me stop and say I've tried to give you a very quick tour of a couple of aspects of poroviscoelasticity and fracture, much of it driven by a mechanics calculation. I hope you found that interesting. Thank you.
We have time for some questions.
Thank you. So in your crack experiments, what was the sample? The specimen, I'm just curious.
What were the same gelatin specimen?
It was, okay, I missed the first part of your talk.
It was,
Okay.
all right.
Okay.
I'll give you one picture.
Okay.
That was the specimen.
Okay. Hydrogels, okay.
Yeah.
Okay. So now in the last part of the talk, when you put that drop of water, and you saw that the crack, the energy dissipation decreased, I also noticed that the crack tip split.
Yeah.
So is there any understanding why that happens? Okay.
Well, every time it split, but there's no understanding of why it did.
Okay. It's also seemed a little asymmetric. So
The splitting looked asymmetric. Yeah.
okay.
It's an experiment.
Okay. Thank you.
Very interesting, thank you. I wonder, do you observe any increasing temperature due to the fracture propagation?
We haven't looked into it. You're saying the energy released must lead to local heating, right?
At the process zone?
Absolutely, but it might be over such a small range, small length scale. It will be difficult to observe.
Thank you.
I had a couple of questions too. You showed the modulus depended on the relative humidity, right? The
Very minor dependence. This way.
yeah, the total the magnitude of the jump.
Initial instantaneous elastic part depends on the yeah.
Is there some microscopic sort of understanding for why that might happen?
Well, the moisture content is different.
Right.
Right.
But in terms of solid molecules moving, not moving, because it seems like that's more like a storage modulus response, instantaneous response, right? So,
well, there is a connection, but I'm not able to tease it out.
all right. And one more quick maybe clarification on when you did this Coleman for the second law
Yeah.
for the constant equation. Did you have to split the stress as did you have to do additive decomposition of sigma E plus sigma V, or how does that?
No. The stress is just the
Oh, so it's still the
total.
Poroviscoelasticity. Okay.
Right.
All right. Okay. Any other questions from
Okay, so this is more of a curiosity. So again, going back to the cracking experiments, you had rather large dissipation energies, right? So that's ductile fracture.
No,
No, it is not. That's what I.
there's no
Plasticity in the.
notion of a plasticity.
Okay. Okay.
There are inelastic strains that are part of the viscous branch.
Okay.
There's no notion of.
Okay. Yeah, that's what I wanted to. Thank you.
And in that case 3 that you showed us, right,
Yeah.
where you had lower loads, did you put the water in there for the last case 4? The load was in that sort of orange block of that diagram you showed.
Yeah, it was.
So the case 4 was case 3 with the water, is that
Yeah,
correct?
right. Case 3 with water before it started.
And again, the reason why this water sort of accelerates the crack, any
So conjecture
conjectures
is that you've allowed water to come in contact with the fracture process zone. It infiltrates into the process zone fairly easily because it's liquid water, not the vapor, right? And it lubricates. It swells. It allows greater mobility for the molecules. The unravel and the crack process speeds up as a result.
Is there a effective opening mode because of the swelling, you think? Or
No, the energy required to move the molecules is now lowered because its mobility is.
so just the mobility is
Yeah.
the only.
Hello. So I was wondering in the last slide when you put this water in the crack, so are you planning to use some other liquid? Because if the liquid is viscous, more viscous, then there will be a lag between crack tip and water tip. So
It's a good idea, but we haven't done it.
okay, because here there is no lag between crack tip and the fluid, but with high viscosity that might be.
This is a 3-component system. It has water and glycerol already in there. Water is low viscosity, so it's easier to infiltrate into it,
Yeah.
and it's going to be a greater lubricant to make the molecules move faster. If you put glycerol in there, it's going to take a longer time period for it to infiltrate into the process zone. So I think the effect may be clouded more into the viscous process and not that easy to unravel.
Okay.
Yeah,
Thank you.
but it's a good thought. We'll think about doing some experiments in that direction.
Any particular reason why you chose glycerol? I mean, just with water, couldn't it
Yeah.
have been possible?
Yeah, I mentioned why we use glycerol.
I missed that part. Could you please repeat?
These experiments were done over a period of a week at room temperature. So this was for the local bacterial colonies, and so we didn't want to heat up our specimen.
I see.
It also controls the viscosity of the overall mixture, and so a couple of reasons for it.
All right. Thank you.
And well, maybe a third one is in practical use, they always use glycerol as an agent for making the flow characteristics slower.
Yes.
Thank you.
Similar question. So, by adding glycerol, is there any change of network structure compared to?
Yeah. Glycerol is not a good solvent for collagen, so they don't mix. And what happens then is that the water acts as a protective barrier. The collagen is immediately attached with the water, and then the glycerol is attached to the water on the other side. So there are pockets of glycerol, pockets of water, but it's at a scale that's so small you don't see that in the continuum scale. You just see the net effect of a material that has a greater viscous response.
Okay, so let's just thank our speaker again.
Thank you.